What if everything you've ever known about the universe, the way space stretches, the way time flows, even the way gravity pulls, was just a fraction of the real story? Picture this: the dimensions we experience every day, the length, width, and depth of the world around us, might be nothing more than the surface of something far stranger, far grander. Hidden beneath the fabric of reality could lie 26 dimensions, curled and twisted into shapes beyond our imagination, influencing everything from the tiniest particles to the vast expanse of the cosmos. This isn't science fiction. It's a cutting-edge theory that could rewrite the rules of physics as we know them. Think about the last time you looked up at the night sky, marveling at the stars. What if I told you that what you're seeing is only a shadow of the universe's true complexity? For decades, scientists have grappled with mysteries that defy explanation: why gravity is so weak compared to other forces, how particles behave at the quantum level, even the very nature of dark matter and energy. The answer to these puzzles might not lie in the dimensions we can see, but in the ones we can't. String theory, one of the most ambitious frameworks in modern physics, suggests that these hidden dimensions aren't just mathematical quirks. They could be the missing pieces of a cosmic puzzle, shaping the universe in ways we're only beginning to grasp. So why does this matter to you? Because understanding these dimensions isn't just about unlocking the secrets of the cosmos, it's about redefining what's possible. Imagine a future where we harness the geometry of higher dimensions to travel farther, uncover new energies, or even peer into the birth of the universe itself. This journey won't be easy. It will challenge everything we think we know, bending our minds as much as it bends space-time. But that's the thrill of discovery, venturing into the unknown, where the rules are still being written. So buckle up. By the end of this video, the universe might not look the same way it did when you pressed play. You wake up every day moving through 3 dimensions, left and right, forward and backward, up and down, while time carries you inexorably forward. These 4 dimensions shape your entire experience of reality. But what if they're just the tip of the iceberg? Imagine a sheet of paper. To a tiny ant crawling across it, the surface seems flat and two-dimensional. But we know the paper has thickness, a third dimension too subtle for the ant to perceive. Now take that idea and stretch it further. Theoretical physicists propose that our universe might be like that sheet of paper, with hidden dimensions coiled into spaces so unimaginably small, 1 billion times tinier than an atom, that they escape our notice entirely. Why would we need these extra dimensions? Think of the fundamental forces in nature: gravity, electromagnetism, and the nuclear forces. In our familiar 4-dimensional world, they behave very differently from one another. But in higher dimensional space, they could unite into a single, elegant framework, like seeing the full picture instead of just disconnected puzzle pieces. String theory, one of the leading candidates for a theory of everything, relies on these extra dimensions to make the math work. Without them, the equations break down, leaving us unable to explain why particles have mass or how black holes warp spacetime. Here's where it gets mind-bending. These hidden dimensions aren't just random add-ons. Their shapes and vibrations determine the very laws of physics. Picture a guitar string. How its tune changes the note it plays. Similarly, the way these dimensions curl and resonate could dictate why electrons have a certain charge or why gravity is so weak compared to other forces. Some theories suggest there could be as many as 26 dimensions, each with its own unique geometry, silently orchestrating the universe behind the scenes. The next time you drop a ball and watch it fall, remember, gravity's whisper might be echoing through dimensions you'll never see. String theory didn't start out as a quest for hidden dimensions. It began with a simple yet radical idea. What if the fundamental building blocks of the universe weren't tiny dots like the particles we learn about in school, but instead were unimaginably small, vibrating strings? At first glance, this might sound like a poetic twist on physics, but the math behind it revealed something extraordinary. For the equations to hold together, for the theory to make any sense at all, these strings couldn't just wiggle through the 3 dimensions we know. They needed room to move 26 dimensions to be exact. Why 26? It's not a number plucked from thin air. When physicists worked through the calculations, they found that anything fewer caused the math to collapse into contradictions. Think of it like building a bridge. If you leave out even one critical support beam, the whole structure falls apart. Those extra dimensions aren't just padding. They're the scaffolding that keeps the universe from crumbling into mathematical chaos. And here's the wild part. Those dimensions aren't stretched out like the ones we're familiar with. They're curled up, folded into shapes so tiny that even the most powerful particle colliders can't glimpse them directly. But what do these hidden dimensions actually do? Imagine a piano with 26 keys instead of the usual 88. The notes it could play would be entirely different, creating harmonies we've never heard before. In the same way, the vibrations of strings through these dimensions could explain why particles have the properties they do, why an electron has its specific mass, why quarks bind together the way they do, even why gravity behaves so differently from the other forces. It's as if we've been listening to a symphony with half the instruments muted, and now we're finally starting to hear the full composition. This isn't just about tidying up the math either. Those extra dimensions could solve some of the biggest mysteries in physics. Take gravity's puzzling weakness, why it's so much feebler than electromagnetism or the nuclear forces. One compelling idea is that gravity isn't weaker at all. It might just be spilling into those hidden dimensions, diluting its strength in our familiar 4-dimensional slice of reality. Picture a sponge soaking up water. What seems like a small amount on the surface is actually spread throughout its entire structure. String theory's 26 dimensions aren't the end of the story, though. Later refinements whittled the number down to 10 or 11 in other versions of the theory. But the core idea remains: the universe might be far more intricate than we ever suspected, with hidden layers of geometry shaping everything from the spin of a quark to the fate of galaxies. The next time you look at the night sky, remember what you're seeing might just be the surface of a reality with depths we're only beginning to fathom. Why does string theory demand exactly 26 dimensions? It's not because physicists have a fondness for the number, it's because the math leaves no other choice. Picture a tightrope walker balancing high above the ground. If they lean too far in any direction, they'll fall. In the same way, the equations of bosonic string theory, one of the earliest versions of the framework, only hold together if the universe has precisely 26 dimensions. Any fewer and the theory crumbles into mathematical inconsistencies. Any more and the delicate balance vanishes, leaving behind a jumble of contradictions. Here's how it works. At the heart of string theory is the idea that particles aren't just points, they're tiny, vibrating strings. The way these strings oscillate determines the properties of the particles they become, like notes on a musical scale. But for those vibrations to make sense, they need to obey strict mathematical rules. When physicists first worked through these equations, they stumbled upon something startling. The numbers only added up if space-time had 26 dimensions. It wasn't a suggestion, it was a requirement. Without those extra dimensions, the theory predicted impossible scenarios, like particles with negative probabilities or energies that spiraled out of control. Think of it like building a house of cards. If you remove even one card, the entire structure collapses. Those 26 dimensions aren't arbitrary. they're the cards holding the universe's foundation in place. In fewer dimensions, the strings couldn't vibrate in all the ways needed to describe the particles we observe in nature. The math would produce ghosts, phantom particles that break the laws of physics. But in 26 dimensions, everything snaps into focus. The equations stabilize, the contradictions vanish, and suddenly, the theory can describe everything from gravity to quantum mechanics with breathtaking elegance. This isn't just abstract number crunching either. Those extra dimensions have real consequences. They explain why string theory can unify forces that seem utterly unrelated in our everyday experience. In the full 26-dimensional space, gravity and electromagnetism aren't separate phenomena. They're different facets of the same underlying structure, like shadows cast by a single object. It's as if we've been trying to understand a sculpture by only looking at its silhouette. With all 26 dimensions in play, we finally see the full shape of reality. Later versions of string theory whittled the number down to 10 or 11 dimensions, but the core idea remains. The universe's blueprint is written in geometry. The next time you count the 3 dimensions around you, remember there's a hidden architecture beneath it all, one that's been holding the cosmos together since the very beginning. If extra dimensions are woven into the very fabric of reality, why don't we notice them as we go about our daily lives? The secret lies in a process called compactification, a cosmic sleight of hand where these dimensions are folded and twisted into spaces so minuscule they evade even our most advanced instruments. Picture a telephone wire strung between 2 distant poles. From a block away, it appears as a thin, one-dimensional line, but step closer, and you'll see it's actually a cylinder with a circular dimension wrapped tightly around its length. The same principle could apply to the universe's hidden geometry. These curled-up dimensions aren't just tiny, they're unimaginably small, with scales billions of times smaller than an atom. To grasp how this works, imagine an ant crawling across a vast parking lot. From the ant's perspective, the ground seems flat and endless. But if you zoomed in with a microscope, you'd see the rough texture of the asphalt, the microscopic peaks and valleys that were invisible from a distance. In the same way, if we could peer into the fabric of space-time at unfathomable resolutions, we might catch glimpses of these coiled dimensions, vibrating like the strings of a harp. But how do they stay so perfectly hidden? Enter Kalabi-Yau Manifolds' exotic, 6-dimensional shapes that could serve as the universe's hidden scaffolding. These aren't just abstract mathematical curiosities. Their intricate folds and twists determine how particles interact, why forces have the strengths they do, and even how space itself bends. Picture a snowflake's intricate symmetry, but magnified into a geometric labyrinth with dozens of dimensions. That's the level of complexity we're dealing with. Here's where it gets even stranger. The way these dimensions are compactified doesn't just hide them, it actively shapes the laws of physics in our observable universe. Like a kaleidoscope's mirrors fracturing light into patterns, the geometry of Calabi-Yau spaces could split a single, unified force into the 4 distinct forces we know: gravity, electromagnetism, and the strong and weak nuclear forces. Change the shape of these hidden dimensions, and you might rewrite the charge of an electron or the mass of a quark. This raises a tantalizing question. If we could somehow uncurl one of these dimensions, even briefly, what would happen? Theoretically, it could unleash phenomena beyond our wildest imagination: wormholes bridging distant points in space, particles with impossible properties, or even entirely new forces of nature. But for now, they remain locked away, their secrets encoded in the hum of vibrating strings. The next time you glance at the night sky, remember, the universe's full grandeur might be tucked into folds too small for even light to reveal. Kalabi-Yau manifolds sound like something out of an abstract artist's sketchbook, but these intricate shapes could be the hidden architects of reality itself. Imagine trying to describe a snowflake to someone who's never seen ice: the delicate symmetry, the endless variations, the way no two are exactly alike. Now take that complexity and multiply it across 6 dimensions, folding and twisting in ways that defy ordinary geometry. That's the realm of Calabi-Yau spaces, where the extra dimensions of string theory might be curled up, invisible yet indispensable. What makes these shapes so special? They're not just mathematical curiosities, they're the stage upon which the universe's fundamental particles perform. Think of a guitar string: pluck it one way and you get a specific note, pluck it differently and the sound changes. In string theory, the vibrations of these tiny, one-dimensional strings determine whether they become electrons, quarks, or even the carriers of gravity. But for those vibrations to produce the rich variety of particles we observe, the strings need room to wiggle far more than our familiar 3 dimensions provide. That's where Calabi-Yau manifolds come in. Their convoluted geometry offers the perfect playground, allowing strings to oscillate in countless unique ways, each vibration corresponding to a different particle or force. Here's the mind-bending part: the exact shape of a Calabi-Yau manifold could dictate the laws of physics in our observable universe. Picture a maze of microscopic tunnels, where every twist and turn influences how particles interact. One configuration might result in a universe where gravity is stronger, or where electrons have a different charge. It's as if the cosmos rolled a pair of dice at the beginning of time, and the outcome, the particular Calabi-Yau shape that formed, locked in the rules we now take for granted. This idea, known as the landscape of string theory, suggests there could be an almost infinite number of possible universes, each with its own unique physics, all determined by the geometry of these hidden dimensions. Visualizing a 6-dimensional shape is no easy feat, but mathematicians have found clever ways to project them into lower dimensions, like casting shadows of a higher dimensional object. These projections reveal stunning, jewel-like structures, labyrinths of curves and surfaces that seem almost alive. Some resemble intricate knots, others unfold into sprawling networks of tunnels and chambers. Yet no matter how beautiful these renderings are, they're only crude approximations. The true nature of Calabi-Yau spaces exists beyond human intuition, in a realm where geometry dances to the tune of quantum mechanics. The implications are staggering. If we could somehow map the exact Calabi-Yau manifold governing our universe, we might finally understand why particles have the masses they do, why forces behave as they do, even why the cosmos looks the way it does. It would be like discovering the blueprints of reality, hidden in plain sight all along. Until then, these shapes remain one of the most tantalizing mysteries in physics, a reminder that the universe's deepest truths might be written in a language of geometry we're only beginning to decipher. Symmetry isn't just about beauty or balance, it's the hidden language of the universe, a set of rules that govern everything from the spin of an electron to the structure of galaxies. And in the realm of 26 dimensions, symmetry takes on a whole new level of importance. Picture a snowflake. No matter how you rotate it, its pattern stays the same. Now imagine that principle stretched across dimensions we can't even see, where the tiniest shift in geometry could rewrite the laws of physics. That's the power of symmetry in higher dimensional space. At the heart of this lies something called conformal invariance, a fancy term for a profound idea. It means the laws of physics stay the same no matter how you scale them up or down, like a blueprint that works whether you're building a toy model or a skyscraper. In 26 dimensions, this symmetry isn't optional. It's the glue holding the entire theory together. Without it, the equations of string theory would unravel. predicting nonsense like particles moving faster than light or probabilities that don't add up. It's the reason the math demands those extra dimensions in the first place. They're the only way to keep the cosmic symphony in tune. But symmetry isn't just about keeping the math tidy. It's a gateway to discoveries that could shatter our understanding of the universe. Take supersymmetry, a concept that emerged from these higher dimensional frameworks. It proposes that every particle we know has a hidden twin, a shadow partner with different properties. Why? Because in a universe with more dimensions, symmetry operations become richer, more intricate. A rotation in higher dimensional space might swap a particle we recognize for one we've never seen, a sleight of hand hidden in the geometry of reality itself. Breaking these symmetries could be just as revealing as preserving them. Imagine a pane of glass shattering. The cracks follow patterns dictated by the material's hidden weaknesses. In the same way, if the symmetries of 26-dimensional space were to fracture in just the right way, they might explain why we ended up with the exact set of particles and forces we see today. Some physicists speculate that what we call the Standard Model, the catalogue of known particles, might just be the fragments of a much larger, symmetric whole, a broken mirror reflecting only a sliver of the truth. The implications are staggering. If we could detect even a hint of these higher dimensional symmetries, perhaps in the subtle behavior of particles at the Large Hadron Collider or in the faint whispers of gravitational waves, it would be like finding a fingerprint left by the hidden architecture of the cosmos. The next time you marvel at the symmetry of a seashell or a spiral galaxy, remember, the universe might be playing by rules written in dimensions far beyond our sight. Strings might be the building blocks of reality, but what if they're just threads woven into something far larger? Enter Branes, short for membranes, theoretical objects that could exist in dimensions beyond our own. Imagine our universe as a sheet of paper floating in a vast, higher dimensional space called the bulk. We're stuck on that sheet, unable to perceive the full expanse around us, while gravity, the only force that might reach beyond our brain, could be leaking into those hidden dimensions, thinning its influence in our world. This isn't just a wild guess. The Randall-Sundrum model, a groundbreaking framework in theoretical physics, suggests exactly that. Our universe might be a three-dimensional island adrift in a sea of higher dimensions, with gravity's elusive weakness explained by its ability to seep into the bulk. Why does this matter? Because Branes could solve one of physics' most nagging mysteries. Think of the forces of nature like voices in a crowded room. Electromagnetism and the nuclear forces shout loudly, bound to our brain, while gravity whispers because it's spread across dimensions we can't see. It's like trying to hear someone speaking through a wall. The sound is muffled, diluted by the space it has to traverse. If gravity isn't weaker, just stretched thin across unseen dimensions, suddenly its feebleness makes sense. But Branes aren't just passive backdrops. They could be dynamic, even colliding with one another. Picture two sheets of paper drifting in a breeze, slapping together. Some theories suggest such collisions might have sparked the Big Bang itself, igniting our universe in a fiery clash of higher dimensional membranes. It's a cosmic reboot, with every collision potentially birthing a new cosmos with its own laws of physics. Here's where it gets even stranger. If our universe is a brane, there could be others, parallel worlds hovering just out of reach in the bulk, each with its own stars, planets, and perhaps even versions of us. We'd never notice them because everything we know, light, matter, even time, might be locked to our brain like shadows cast on a cave wall. Gravity, though, could be the one signal bleeding through, a faint tug between worlds. The implications are staggering. If we could detect traces of gravity's leakage, perhaps in subtle anomalies in how objects fall or in the ripples of space-time, it would be like finding fingerprints of the bulk. Experiments with ultra-precise gravity measurements or particle colliders might one day reveal these hidden dimensions, not by seeing them directly, but by catching their echo in the behavior of the forces we know. The next time you drop a pen and watch it fall, remember, that gentle pull might be the universe's way of hinting at realms beyond our own. Gravity is the force that keeps planets in orbit and our feet on the ground, yet compared to the other fundamental forces, it's astonishingly weak. A simple fridge magnet can defy the entire gravitational pull of the Earth, lifting a paperclip with ease. Why is there such a staggering mismatch in strength? The answer might lie not in what we see, but in what we don't. Hidden dimensions could be siphoning gravity's power away, spreading it so thin across higher dimensional space that it barely registers in our familiar three-dimensional world. Think of it like a sponge soaking up water. Pour a cup onto a flat table and the liquid pools in one spot. But press that same cup of water into a sponge and it disperses, seeping into every tiny cavity. In our analogy, the table is our three-dimensional universe, while the sponge represents the full higher dimensional space. Gravity isn't weaker, it's just leaking into dimensions we can't perceive, its strength diluted across realms beyond our reach. This idea isn't just theoretical gymnastics. It's a potential explanation for one of physics' most persistent puzzles: why gravity is 10 trillion times feebler than electromagnetism. The key players here are hypothetical particles called gravitons, the carriers of gravity, just as photons carry light, while other force particles like photons or gluons might be confined to our three-dimensional brain. Gravitons could be slipping into the bulk, the higher dimensional space surrounding us. Picture a group of people shouting in a crowded room. If most voices stay near the floor, their sound is loud and clear. But if one voice drifts upward, spreading through the rafters, it becomes faint, almost inaudible. That's gravity in this scenario. Its signal weakened because it's echoing where we can't follow. This isn't just a clever metaphor. It leads to testable predictions. If gravity is indeed leaking into extra dimensions, we might detect subtle deviations in its behavior at extremely small scales. Experiments using ultra-precise torsion balances or microscopic measurements of gravitational force could reveal anomalies, tiny discrepancies from Newton's familiar inverse square law. Some theories suggest that at distances smaller than a millimeter, gravity's grip might strengthen slightly, as if we're getting closer to the source of the leak. It's like hearing that distant voice grow clearer as you step toward the hidden staircase it's drifting down. The implications are profound. If gravity's apparent weakness is a clue pointing to hidden dimensions, confirming it would revolutionize our understanding of the cosmos. It would mean that every time an apple falls from a tree or a planet tugs at its star, we're witnessing not just the pull of mass, but the whisper of a multidimensional universe. The next time you feel gravity's gentle hold, remember, it might be the faintest echo of a force that truly reigns supreme, just not in the dimensions we call home. Proving the existence of hidden dimensions might sound like science fiction, but physicists are hunting for them with tools precise enough to measure the faintest whispers of reality. Picture a detective searching for fingerprints invisible to the naked eye, except in this case, the clues are buried in the fabric of space-time itself. One approach involves probing gravity at astonishingly small scales, where the familiar pull we experience might start behaving differently. If extra dimensions are curled up at microscopic sizes, gravity could strengthen just slightly at distances less than a millimeter, as if we're glimpsing the edge of where it begins leaking into unseen realms. Experiments like these use delicate torsion balances, devices so sensitive they can detect forces tinier than the weight of a single bacterium, searching for any deviation from Newton's centuries-old law. But gravity isn't the only messenger. Particle colliders like the Large Hadron Collider might also catch traces of higher dimensions in action. When protons smash together at nearly the speed of light, the energy released could, for a split second, create particles that only exist if extra dimensions are real. Imagine throwing a pebble into a pond and watching the ripples. Normally, you'd expect circular waves, but if the pond had hidden grooves or channels, the ripples might warp in unexpected ways. Similarly, if collisions at the LHC produce energy that suddenly vanishes, it could mean particles are escaping into dimensions we can't see, like echoes fading into unseen corridors. Then there's the cosmos itself, which might hold signatures of dimensions beyond our perception. If our universe is a brane floating in a higher dimensional bulk, collisions with other branes could have left imprints in the cosmic microwave background, the afterglow of the Big Bang. It's like finding scratches on a window pane, hinting at objects moving just outside our view. Some theories even suggest that such collisions could generate gravitational waves with unique patterns, ripples in spacetime that future observatories might detect, carrying encrypted messages from the bulk. The challenge, of course, is that these dimensions, if they exist, are masters of disguise. They hide in the gaps between measurements, the margins of error, the unexplained flickers in data. Yet every null result, every experiment that doesn't find what it's looking for, still teaches us something. Like mapping an invisible maze by bouncing sound waves off its walls, each failed attempt narrows the possibilities, inching us closer to the day when the universe's hidden architecture might finally snap into focus. Until then, the hunt continues, a testament to human curiosity's power to chase shadows, and perhaps one day catch them. Black holes have long been the universe's ultimate enigmas, cosmic traps where gravity reigns so absolute that not even light can escape. But what if these celestial monsters are hiding more than just crushed matter and warped space-time? In a universe threaded with hidden dimensions, black holes might not play by the rules we've come to expect. Their very existence could be a backdoor, a way to glimpse the geometry of realms beyond our perception. Take Hawking radiation, the faint glow theorized to escape black holes as they slowly evaporate. In our familiar four-dimensional world, this process is achingly slow. A supermassive black hole might take longer than the current age of the universe to vanish. But introduce extra dimensions and the math shifts dramatically. Gravity, already leaking into those unseen folds, could pull harder near a black hole's event horizon, accelerating its evaporation like water boiling off a hot pan. Some models suggest that in higher dimensional space, tiny black holes might explode with the energy of atomic bombs, their death throws flashing like cosmic beacons, signaling the presence of dimensions we can't see. Then there's the singularity, the infinitely dense core where Einstein's equations break down. In a four-dimensional universe, it's a point of no return, a place where physics as we know it ceases to exist. But add extra dimensions and the singularity might unravel into something stranger, a sprawling, higher dimensional structure, perhaps a vibrating string or a writhing brain. It's like comparing a pinprick to a tangled, not the same object, viewed through entirely different lenses. Here's where it gets even wilder. If extra dimensions exist at scales larger than a Planck length, something string theory allows particle colliders like the Large Hadron Collider might one day create micro-black holes. These wouldn't be the planet-swallowing beasts of deep space, but fleeting, quantum-sized distortions, popping in and out of existence like bubbles in a boiling pot. Their formation would be smoking gun evidence for hidden dimensions, a sign that gravity's true strength is concentrated where we least expect it, of course, no one has spotted a micro black hole yet. But their absence isn't proof against extra dimensions, just a clue that if they exist, they're curled tighter than we've probed so far. The search continues, with each new collision at the LHC a roll of the cosmic dice. Meanwhile, astrophysicists scour the skies for black holes behaving oddly, evaporating too fast, spinning in unexpected ways, or emitting gravitational waves with peculiar echoes. Any deviation from Einstein's predictions could be a fingerprint of higher dimensional physics, a whisper from the universe's hidden blueprint. So the next time you picture a black hole as a simple void in space, remember, it might be far more than a cosmic trash compactor. It could be a key, a crack in reality's facade, offering us a glimpse into the dimensions that shape everything without us ever knowing they were there. Dark matter is the universe's most stubborn ghost, an invisible substance that outweighs ordinary matter 5 to 1, shaping galaxies and bending light with its gravitational pull, yet refusing to reveal itself in any other way. For decades, scientists have chased it through underground detectors and particle colliders, always coming up empty. But what if we've been looking in the wrong places entirely? What if dark matter isn't hiding in our dimension at all, but drifting just beyond it, tethered to us only by gravity's faintest threads? This wild idea starts with a simple twist. Dark matter might be ordinary matter from a neighboring brane, a parallel universe hovering millimeters away in higher dimensional space. Think of two sheets of paper stacked so close they almost touch. Ants crawling on one sheet would never notice the ants on the other, but if one colony dropped crumbs, the others might feel the faintest tug as they fell through the gap. In this scenario, dark matter could be stars, planets, even entire civilizations right next door, yet forever out of reach because their light and forces can't cross the dimensional divide. Only gravity seeping through the bulk would let us sense their presence, like neighbors communicating through whispers through a shared wall. But there's another possibility. Dark matter might not be entire galaxies in another dimension. It could be single particles that move through extra dimensions we can't see. Picture a mosquito buzzing around a room. To us, it seems to dart left and right, forward and back. But to a hypothetical two-dimensional creature living on the floor, that mosquito would vanish and reappear mysteriously as it moved up and down into the third dimension they can't perceive. In the same way, dark matter particles might wiggle into hidden dimensions, making them flicker in and out of our observable universe. Their mass would anchor them to our reality through gravity, but their other interactions could be spread across dimensions we'll never directly observe. This isn't just poetic speculation. The math holds up. Some theories suggest that if extra dimensions exist, they could host entire families of particles called Kaluza-Klein modes, echoes of known particles vibrating at higher frequencies, like notes played on a string too high for us to hear. These shadow particles could have the exact properties we attribute to dark matter, massive enough to bend space-time, yet nearly invisible because their interactions are diluted across dimensions. It's as if we've been searching for a missing cat in our house, only to realize it's been sunbathing on the roof the whole time, a place we never thought to look. The implications are staggering. If dark matter is tied to extra dimensions, discovering it could crack open two cosmic mysteries at once. Experiments like the Large Hadron Collider might one day produce particles that briefly vanish, their energy bleeding into higher dimensions like water spiraling down a drain. Or gravitational wave detectors could catch anomalies, ripples in spacetime that don't match any known astrophysical event, hinting at collisions or structures in a parallel brane. Even the distribution of dark matter in galaxies, which often clumps in ways that defy predictions, might make perfect sense if it's influenced by geometries we can't yet map. Of course, not all physicists are convinced. Some argue that extra dimensions are an elegant solution in search of a problem, and that dark matter could still turn out to be a yet undiscovered particle within our own dimensional playground. But that's the beauty of science. The universe keeps its secrets close, revealing them only when we ask the right questions. Whether dark matter is a shadow from another dimension or something stranger still, one thing is certain: the answer will rewrite the story of the cosmos. And when it does, we might find that the invisible hand shaping our universe has been reaching out from places we never thought to look. What if everything you see around you, the depth of a canyon, the curve of a galaxy, even the space between your fingers, was nothing more than an elaborate illusion? The holographic principle turns our understanding of dimensions on its head, suggesting that our three-dimensional reality might be a shadow cast by information encoded on a distant, two-dimensional surface. It's like watching a movie in 3D. The glasses trick your brain into seeing depth, but peel them off, and you're left with a flat screen. In this cosmic twist, the universe itself could be the ultimate optical trick, with extra dimensions emerging not as physical spaces, but as patterns in a deeper, more fundamental code. This idea didn't come from nowhere. It sprouted from the paradoxes of black holes, those cosmic enigmas where gravity crushes matter into oblivion. When physicists like Jacob Bekenstein and Stephen Hawking studied these voids, they stumbled on something bizarre. A black hole's entropy, a measure of its hidden information, seemed tied not to its volume but to the area of its event horizon. It was as if all the data swallowed by the black hole wasn't lost inside but smeared across its surface like a celestial hard drive. From this revelation, a radical thought emerged. If a black hole's interior could be described entirely by information on its boundary, why not the entire universe? Here's where it gets dizzying. If the holographic principle holds, the extra dimensions we've been searching for might not be real in the traditional sense. Instead, they could be emergent, like the way temperature emerges from the chaotic dance of molecules, even though no single molecule is hot. In this view, higher dimensions aren't places you could travel to. They're side effects of quantum information processing on a vast two-dimensional canvas. Picture a video game. The lush 3D world you explore isn't stored in your console as a miniature landscape. It's rendered in real time from lines of flat, binary code. Our universe might work the same way, with the third dimension unfolding from data etched on some distant cosmic horizon. But how could this possibly work? One clue lies in quantum entanglement, that spooky connection where particles instantly influence each other across vast distances. Some theorists suggest this phenomenon hints at the underlying 2D structure of reality, like threads stitching together the illusion of depth. It's as if the universe is a tapestry, and what we perceive as space is just the weave of countless entangled threads. Even gravity, the force that sculpts galaxies, might be a secondary effect, a byproduct of information flow on the boundary, like ripples spreading across the surface of a pond while the true action happens beneath. The implications are staggering. If the holographic principle is correct, it means the search for hidden dimensions isn't about finding new places to explore, but decoding the rules of a cosmic projection. Experiments like Fermilab's holometer have already tried to detect the pixelation of space-time tiny graininess that might betray its digital origins. So far, no luck, but if future instruments ever catch that flicker in the fabric of reality, it would mean that everything, from the stars above to the device in your hand, is just a hologram, a shimmering mirage painted by the universe's deepest, most mysterious code. The next time you reach out to touch something, pause. That sensation of solidity, of distance, might be the most convincing illusion of all, a trick played by dimensions that don't truly exist, but somehow feel as real as your own breath. We experience time as an unbreakable arrow always marching forward, never bending back. But what if that's just a simplification, a flattened version of something far more intricate? Hidden dimensions might hold the key to time's deepest mysteries, reshaping it from a straight line into a sprawling, multidimensional labyrinth. Think of it like watching a shadow puppet show. The shapes dancing on the wall seem flat and simple, but behind the scenes, the puppeteer's hands move through three-dimensional space, twisting in ways the audience can't see. Time as we know it could be just as much of a shadow, a projection of richer, more complex temporal structures vibrating in dimensions beyond our perception. This isn't just speculation. Some theories, like those emerging from string theory and quantum gravity, suggest that time's arrow, its stubborn insistence on moving in one direction, might arise from the way higher dimensional geometries fold and interact. Picture a river flowing downhill. From our limited perspective, the water's path seems inevitable, dictated by gravity. But zoom out, and you'd see the river's course was shaped by the entire landscape, the mountains, valleys, and hidden aquifers feeding it from below. Similarly, time's flow could be sculpted by unseen dimensional contours, with entropy and causality emerging from their hidden architecture. Then there's the enigma of closed time-like curves, theoretical loops in space-time that could, in principle, allow time travel. In a four-dimensional universe, these curves are fragile, demanding conditions so extreme they border on fantasy. But introduce extra dimensions and suddenly the math shifts. Higher dimensional geometries could twist space-time into stable, self-reinforcing loops, like a Möbius strip where time folds back on itself without paradox. It's as if we've been trying to tie a knot with a single thread, only to realize that with extra strings, the knot holds effortlessly. Quantum mechanics adds another layer of strangeness. At the smallest scales, particles don't seem to experience time the way we do. Entanglement, superposition, and even quantum jumps suggest a reality where time is fluid, reversible, or even illusory. Hidden dimensions might explain this dissonance, offering a stage where quantum processes play out in higher temporal realms, only projecting their consequences into our linear experience. Imagine a conductor leading an orchestra. The musicians might play complex, interwoven rhythms, but from the audience you only hear the unified melody. Our perception of time could be that melody, an oversimplification of a far richer symphony. The implications are staggering. If time is a higher dimensional phenomenon, it could redefine everything from the Big Bang to the heat death of the universe. The moment of creation might not have been a single point but a multidimensional event, like a stone dropped into a pond with more than 3 dimensions, sending ripples we're still decoding. Even our sense of free will could be reshaped not as an illusion, but as a negotiation between the linear time we experience and the branching, multidimensional time we don't. So the next time you check your watch, remember, those ticking seconds might be the faintest echo of something far grander, a rhythm woven into the hidden geometry of reality itself. Parallel universes might not be the stuff of science fiction after all. They could be lurking just a whisper away in the hidden dimensions we've been exploring. Picture our universe as a slice of bread floating in a cosmic loaf, with countless other slices stacked alongside it, each hosting its own stars, planets, and perhaps even life. This is the brain multiverse, a mind-bending extension of string theory where entire universes exist as membranes, brains for short drifting through a higher dimensional space called the bulk. The eerie part, we'd never know they're there, light and matter might be trapped on their own branes, like actors performing on separate stages, unaware of the theaters standing right beside them. But how could such a multiverse work? Imagine two soap bubbles floating in the air. If they collide, they might merge or bounce apart, sending ripples across their surfaces. Now replace those bubbles with branes, and you've got a potential explanation for the Big Bang itself. Some theories suggest our universe wasn't born from a single point of infinite density, but from a cataclysmic collision between branes in the bulk, a cosmic car crash that unleashed the energy to spark stars, galaxies, and everything we know. This cyclical model, called the ekpyrotic universe, implies that the Big Bang wasn't a one-time event but a recurring phenomenon, with universes rising and falling like tides in an unseen sea. Here's where it gets even wilder. Each of these brane universes could operate under entirely different laws of physics. Ours is fine-tuned for life, with just the right constants to allow atoms, chemistry, and consciousness. But on another brane, gravity might be stronger, electromagnetism weaker, or the very concept of time might unravel differently. It's like tuning a radio. Our universe is set to one frequency where life can exist, while others are lost in static or broadcasting realities we can't begin to fathom. Some might be barren, their physics too chaotic for structure. Others could harbor forms of matter or energy we've never dreamed of. The implications ripple far beyond theory. If brane collisions can spawn universes, our cosmos might bear scars from that ancient encounter. Patterns etched into the cosmic microwave background, the afterglow of the Big Bang. Astronomers have already spotted curious anomalies in this radiation, like cold spots or strange alignments that defy standard explanations. Could these be fingerprints of a pre-bang event, echoes of a brane collision imprinted on the infant universe? Future telescopes, like the James Webb successors, might one day find the smoking gun a telltale pattern in the sky that points to a larger, multidimensional reality. And then there's the ultimate question: could we ever detect these parallel worlds directly? If gravity truly leaks into the bulk, as some models suggest, then the gravitational pull of a neighboring brane might subtly tug on our own. It's a long shot, but ultra-sensitive detectors could one day catch whispers of these hidden universes, an unexplained warp in space-time, a gravitational wave with no known source, or even a particle that vanishes inexplicably, slipping into another dimension like a ghost through a wall. The brane multiverse transforms the cosmos from a solitary existence into a bustling neighborhood, teeming with universes, each dancing to their own tune. Whether they're barren wastelands or thriving alien realms, their very possibility reshapes our place in existence. We might never visit these parallel worlds, but their shadows could be all around us, hidden in the math, the sky, and the very fabric of reality, waiting for the right moment to reveal themselves. Quantum entanglement has baffled scientists for nearly a century. Particles separated by vast distances instantly influencing each other, as if space and time don't apply to them. Einstein famously called it spooky action at a distance, a phenomenon so strange it seemed to break the rules of reality. But what if the spookiness vanishes when we stop thinking in 3 dimensions? Hidden geometries could be the missing piece, offering shortcuts through higher dimensional space that make entanglement feel almost ordinary. Imagine 2 ants crawling on opposite ends of a folded piece of paper. To them, the distance seems vast, but fold the paper just right, and their positions suddenly touch. In our 3-dimensional world, entangled particles appear impossibly far apart. Yet if extra dimensions exist, their connection might be as simple as those ants brushing antennae through a hidden fold. This isn't just a metaphor, it's a potential bridge between quantum mechanics and general relativity, 2 pillars of physics that have stubbornly refused to reconcile. The math hints at something extraordinary. In string theory, higher dimensional geometries like Calabi-Yau manifolds don't just house curled-up dimensions. They could also create tunnels or wormholes on microscopic scales. These wouldn't be the sci-fi kind you could fly a ship through, but far subtler structures woven into the fabric of space-time itself. When particles become entangled, their quantum states might link through these hidden passageways, bypassing the linear distance we perceive. It's as if the universe handed them a backstage pass, letting them communicate through dimensions we can't see. Here's where relativity enters the picture. Einstein taught us that nothing travels faster than light, but entanglement appears to defy that. Unless, of course, the particles aren't truly traveling anything at all. If their connection routes through higher dimensions, the speed limit stays intact. No information rushes between them. They're simply tapping into a deeper layer of reality where separation works differently. Think of two people video calling from opposite sides of the planet. The delay feels instantaneous, not because the signal breaks physics, but because it takes a smarter path through satellites and fiber optics, not straight through the Earth. The implications ripple across physics. If entanglement relies on hidden dimensions, it could explain why quantum effects seem to collapse when observed. Measurement might anchor particles back to our familiar 3D slice, severing their higher dimensional link like cutting a puppet's strings. Even the notorious measurement problem, the mystery of why observation changes quantum states, could shift from a philosophical quandary to a geometric one. The act of observing might not be magical. It could simply force particles to choose a position in our limited dimensions, snapping the extra-dimensional threads that connected them. Experiments are already probing this wild idea. Quantum computers, which rely on entanglement to perform calculations, could inadvertently reveal fingerprints of higher dimensions if their qubits behave in unexpected ways. Gravitational wave detectors, too, might catch anomalous subtle tremors in spacetime that hint at structures too small or too twisted for our instruments to see directly. Even tabletop experiments with entangled photons could uncover statistical quirks that point to hidden geometric connections. Of course, not every physicist is convinced. Some argue that extra dimensions are an elegant solution in search of evidence, and that entanglement's mysteries might yield to other explanations. But that's the thrill of science. The universe keeps its secrets close, revealing them only when we ask the right questions. Whether entanglement's spookiness stems from hidden dimensions or something stranger still, one thing is clear: the answer won't just solve a quantum puzzle. It could rewrite our understanding of reality itself, showing us that the threads connecting the cosmos are far more intricate and far more beautiful than we ever dreamed. The universe could have taken countless forms with more dimensions, fewer, or even none at all. Yet here we are, in a cosmos where space stretches in 3 directions and time marches forward, surrounded by the precise conditions needed for stars, planets, and life itself. This isn't just luck. It might be the only way things could have turned out if beings like us were ever to ask the question. That's the essence of the Anthropic Principle. The universe appears finely tuned for life because, well, we're here to notice it. And when it comes to those 26 hidden dimensions, this principle could explain why they're not just mathematical curiosities, but cosmic necessities. Take a step back and consider the alternatives. In a universe with fewer dimensions, say, only 2, gravity would behave so differently that planets couldn't form stable orbits. Stars would either collapse too quickly or never ignite at all. Even chemistry would break down, with atoms unable to bond in ways that create complex molecules. On the flip side, a universe with too many large, visible dimensions would dilute forces like gravity and electromagnetism to the point where matter couldn't clump together at all. Galaxies would never coalesce, and life as we know it would be impossible. It's like building a house of cards. Remove one card and the structure collapses. Add too many and it becomes a tangled mess. 26 dimensions, it turns out, might be the sweet spot where the math holds firm and the physics allows for observers like us to exist. But why that specific number? Here's where string theory's equations become eerily precise. Just as a guitar string needs to vibrate at certain frequencies to produce musical notes, the strings of string theory require a specific number of dimensions to avoid mathematical chaos. In fewer than 26, the theory predicts probabilities that don't add up or particles with impossible properties like negative mass or faster than light speeds. It's as if the universe's code contains error-checking rules, and 26 dimensions are the only setting where the program runs without crashing. The Anthropic Principle kicks in because out of all possible configurations, this one doesn't just work, it permits the stable atoms, predictable gravity, and intricate chemistry that life demands. Think of it like a cosmic lottery. Imagine countless universes, each with different dimensional blueprints. Most are barren, their physics too chaotic or too sterile to support complexity. But a rare few like ours land on the perfect combination where particles can form, stars can shine, and minds can ponder their own existence. We're not just passive bystanders in this scenario. Our very presence is a clue, a signpost pointing to why this particular arrangement of dimensions isn't just possible, but inevitable. The implications stretch beyond theory. If the Anthropic Principle holds, it suggests that other universes, with different numbers of dimensions or physical laws, might truly exist, even if they're forever beyond our reach. Some could be stillborn, collapsing instantly under their own contradictions. Others might harbor forms of life so alien, they're built from entirely different rules. But here, in this corner of the multiverse, we've hit the jackpot. A universe where the math and the molecules align just right, allowing us to gaze at the stars and wonder why they shine at all. So the next time you marvel at the night sky, remember, you're not just looking at a random assortment of lights. You're seeing the echoes of a cosmic balancing act, a universe that bent its own rules in 26 dimensions just so you could be here to see it. And that's a story far grander than any fiction. The idea that our universe might harbor hidden dimensions didn't spring from modern string theory. It took root nearly a century ago when two physicists dared to reimagine reality itself. In 1921, Theodore Kaluza, a little-known mathematician, sent a letter to Albert Einstein that would shake the foundations of physics. He proposed a radical solution to the puzzle of unification. What if electromagnetism wasn't a separate force, but the shadow of a fifth dimension curled into a circle so small it escaped detection? Einstein, initially skeptical, was stunned when the math held up. Overnight, Kaluza's extra dimension became the first bridge between gravity and electromagnetism, hinting that the cosmos might be far more expansive than anyone had dreamed. But it was Oscar Klein who gave the theory its legs in 1926. He realized that if this fifth dimension were compactified, curled up at scales a billion times smaller than an atom, it would explain why we only perceive 4 dimensions in daily life. Picture a garden hose stretched across a field. From a distance, it looks like a one-dimensional line, but up close, you see its circular cross-section. Klein's refinement transformed Kaluza's speculative leap into a tangible framework, proving that extra dimensions weren't just mathematical fluff. They could have real, measurable consequences. For decades, the Kaluza-Klein theory languished on the fringes of physics. The equations were elegant, but without experimental proof or a quantum framework, the idea seemed like a beautiful dead end. Then, in the 1970s, string theory revived it with a twist. Physicists realized that strings' tiny, vibrating filaments couldn't dance in just 4 dimensions. The math demanded more, first 10, then later 26. Suddenly, Kaluza and Klein's 5th dimension wasn't an anomaly. It was the tip of an iceberg with entire hidden geometries waiting to be mapped. What's striking about this journey is how each generation built on the last. Kaluza and Klein's work was dismissed as fringe science until string theorists uncovered its hidden potential. Their 5th dimension became the prototype for the curled-up Kalabi-Yau manifolds we now study. Even their compactification idea, once seen as a clever trick, is now foundational to modern physics. It's a reminder that breakthroughs often begin as heresies, with ideas too radical to accept until the math forces us to see differently. Today, as we grapple with 26 dimensions, we're standing on the shoulders of those early visionaries. The questions have grown more complex, but the spirit remains the same: to uncover the universe's hidden layers, no matter how improbable they seem. The next time someone dismisses an idea as too wild, remember Kaluza and Klein's unseen dimension was once considered fantasy. Now, it's the bedrock of theories that could redefine reality itself. Of course, not everyone is convinced that hidden dimensions, let alone 26 of them, hold the key to the universe's deepest secrets. Some physicists raise a fair point. If a theory can't be tested, is it really science? String theory, for all its mathematical elegance, has yet to produce a definitive prediction that experiments can confirm or deny. Unlike Einstein's general relativity, which predicted the bending of starlight around the sun, later confirmed during a solar eclipse, string theory's extra dimensions remain frustratingly out of reach, tucked into scales too small for even our most powerful particle colliders to probe. Critics argue this isn't just a technical hurdle, it's a fundamental flaw. Science, after all, advances by making bold claims that can be proven wrong. If a theory is too flexible, too adaptable to explain any observation, does it actually explain anything at all? Then there's the problem of compactification. Even if extra dimensions exist, the way they're folded, their precise shapes and sizes, seems arbitrary. String theory allows for a staggering number of possible configurations, perhaps 10 to the 500 or more. Each one could lead to a universe with entirely different physics. Some physicists see this as a feature, a landscape of possible realities where ours is just one lucky winner. Others call it a cop-out, a way to dodge the hard work of narrowing down the options. Imagine walking into a shoe store where every pair fits perfectly, no matter your size. Convenient, absolutely, but it also means the store isn't telling you much about your feet. But let's be fair, every groundbreaking theory faces skepticism. Quantum mechanics was once dismissed as absurd for suggesting particles could be in 2 places at once. Black holes were considered mathematical oddities until we started photographing them. The real test isn't whether a theory has critics, but whether it keeps pushing us to ask better questions. And string theory, for all its unknowns, has done exactly that. It's forced us to rethink the nature of space, time, and even information itself. The holographic principle, born from string theory's puzzles, has reshaped how we think about black holes and the fabric of reality. Here's the thing, science doesn't progress in straight lines. Sometimes the most revolutionary ideas take decades or longer to find their footing. The math behind 26 dimensions isn't just pretty equations. It's a toolkit for exploring possibilities we'd never considered. Maybe the critics are right, and string theory will eventually give way to something even stranger. Or maybe, like Kaluza and Klein's forgotten 5th dimension, it's ahead of its time, waiting for the right moment to click into place. Either way, the debate itself is a sign of healthy science, a field alive with curiosity, where even the wildest ideas are worth chasing, if only to see where they lead. String theory's vision of hidden dimensions is dazzling, but it's not the only game in town when it comes to uniting gravity and quantum mechanics. Enter loop quantum gravity, a radical alternative that cuts the cosmic deck in an entirely different way. Instead of adding dimensions, this framework suggests spacetime itself is woven from tiny, indivisible loops, a fabric stitched together by quantum threads so small, they redefine what here and now even mean. Picture the universe not as a stage with hidden trapdoors, but as a tapestry where every stitch is a quantum knot, vibrating with the energy of existence itself. The clash between these two theories isn't just academic, it's a battle over the soul of reality. String theory's extra dimensions offer elegance, a way to harmonize all forces as vibrations in higher dimensional space. But loop quantum gravity dismisses that as unnecessary baggage. Why invent unseen dimensions, it argues, when the answers might lie in the quantum structure of the three dimensions we already have? It's like trying to fix a watch by building a whole new clock tower versus taking apart the gears to see how they truly mesh. Here's how loop quantum gravity works. Imagine spacetime as a mesh of interconnected loops like a cosmic chainmail. These loops aren't embedded in space, they are space, with each link representing the smallest possible unit of volume, a billion times smaller than an atom. Time, too, becomes granular, advancing in tiny, discrete jumps rather than a smooth flow. The result, a universe where black holes don't collapse into singularities but rebound like quantum springs, and where the Big Bang might not be a beginning but a bounce from a previous cosmic cycle. The implications are profound. While string theory dances with hidden dimensions to explain gravity's weakness, loop quantum gravity suggests gravity emerges from the spin of these spacetime loops, like how the warmth of sunlight arises from countless photons, even though you never see the individual particles. There's no need for gravity to leak into extra dimensions. Its quirks could just be the way quantum spacetime stitches itself together. Yet for all its brilliance, loop quantum gravity has its own blind spots. String theory excels at unifying forces, weaving electromagnetism and the nuclear forces into gravity's tapestry. Loop quantum gravity, by contrast, struggles to incorporate those other forces as seamlessly. It's like having a perfect theory of canvas but no paint to explain the universe's colors. And while string theory's extra dimensions remain unproven, loop quantum gravity's granular spacetime hasn't yet been detected either, though some hope that faint imprints in the cosmic microwave background or anomalies in gravitational waves might one day reveal its quantum knots. This isn't just a technical debate, it's a philosophical fork in the road. String theory whispers that reality is grander than we perceive, with hidden layers waiting to be uncovered. Loop quantum gravity counters that the truth might be subtler, lurking in the quantum grain of the ordinary. Both demand we rethink everything we know about space, time, and existence. And that's the beauty of theoretical physics. Even when the answers elude us, the questions stretch our minds across the cosmos. So which approach will prevail? Perhaps neither or both. The history of science is littered with rival theories that later merged into something deeper, like waves and particles uniting in quantum mechanics. Whether spacetime is built from strings, loops, or some yet undiscovered structure, one thing's certain: the universe's secrets won't give themselves up easily. But the hunt itself, that's where the magic happens. What if the universe isn't just described by math? What if it is math? The moment we entertain the idea of 26 dimensions, we're forced to grapple with a haunting possibility. that numbers and equations aren't just tools for understanding reality, but the very foundation of reality itself. This isn't some abstract thought experiment. Physicists like Max Tegmark argue that the universe might literally be a mathematical structure, with hidden dimensions serving as proof that existence is, at its core, an intricate web of relationships waiting to be decoded. Think of it like a video game. The worlds we explore on screen aren't physical, they're built from code, from pure information. Could our cosmos operate the same way, with extra dimensions as lines in a cosmic program we're only beginning to read? But here's the twist. If dimensions are just mathematical constructs, why do they feel so concrete? We measure them, navigate them, even build technologies reliant on their consistency. This dilemma splits thinkers into two camps. On one side, the realists insist dimensions are as tangible as the ground beneath your feet, physical properties of the universe waiting to be mapped. On the other, the instrumentalists argue they're merely useful fictions, frameworks we invent to make sense of the chaos. It's the difference between believing a map is the territory and admitting it's just a handy approximation. When you drop an apple, does it fall because gravity warps a four-dimensional space-time, or because the math says it should? And why does that distinction even matter? The debate spills into metaphysics when we ask why these dimensions exist in the first place. Some theories suggest they're inevitable, the only possible outcome of self-consistent mathematical laws. Others propose they're contingent, accidents of cosmic history that could have been different. Imagine a universe where time had two arrows instead of one, or where quantum entanglement arose from 7 curled-up dimensions instead of 26. Would the math still work? Would observers in that universe swear their version was the only logical one? The Anthropic Principle looms large here. Our very presence as conscious beings might be filtering our perception, making certain dimensional arrangements seem inevitable when they're just one possibility in a vast multiverse of options. This isn't just academic navel-gazing. The way we answer these questions shapes how we search for truth. If dimensions are real, then discovering them becomes a matter of better instruments and sharper experiments. But if they're models, we might forever be refining approximations, chasing shadows on a cave wall. The irony, both paths lead to progress. Quantum mechanics thrived by abandoning the idea of particles having definite positions until measured, embracing probability over certainty. Hidden dimensions could demand a similar leap, a willingness to accept that real might not mean what we think it means. So where does that leave us? Perhaps the most humbling realization is that reality, whatever it is, doesn't owe us intuitive satisfaction. The universe operates by rules that may forever hover at the edge of comprehension, with 26 dimensions as a reminder that the deeper we dig, the stranger and more beautiful the truth becomes. Long before physicists scribbled equations about curled-up dimensions, artists and writers were already painting worlds beyond the familiar three. Take Edwin Abbott's 1884 classic Flatland, where two-dimensional squares and circles grapple with the mind-bending arrival of a sphere from the third dimension. It wasn't just a whimsical tale, it was a thought experiment, forcing readers to confront how limited perception shapes reality. Abbott's flat shapes couldn't conceive of up or down, just as we might be blind to higher dimensions woven into our own world. This tension between what we experience and what might lie beyond has fueled creative minds for generations, turning abstract math into gripping stories that, sometimes uncannily, foreshadow science's later discoveries. Science fiction didn't stop at metaphor. By the mid-20th century, authors like H.G. Wells and Madeleine L'Engle were weaving extra dimensions into their plots not as curiosities but as gateways. A wrinkle in time introduced the tesseract, a four-dimensional hypercube, as a cosmic shortcut, folding spacetime like origami. Decades later, physicists would explore similar ideas with wormholes and Calabi-Yau manifolds. It's as if fiction handed science a blueprint, saying, here's one way it could work. Even Interstellar, with its stunning portrayal of a five-dimensional bulk, drew direct inspiration from Kip Thorne's real-world relativity equations, proving that the line between speculative art and cutting-edge theory is thinner than we think. But why does this crossover matter? Because imagination often leaps ahead of proof. When the Twilight Zone episodes or Doctor Who arcs played with alternate realities and dimensional rifts, they weren't just entertaining, they were priming audiences to think in multidimensional terms. Consider Stranger Things Upside Down, a parallel dimension eerily similar to our own, yet governed by different rules. The show's creators didn't invent the concept. They tapped into century-old physics debates about branes and multiverses, repackaging them as binge-worthy drama. In doing so, they made esoteric ideas visceral, letting viewers feel the strangeness of hidden dimensions rather than just hear about them in a lecture hall. Pop culture's influence runs both ways. When Star Trek first visualized warp drive bending space, it inspired physicists like Miguel Alcubierre to draft actual models for faster-than-light travel. Similarly, the idea of hyperspace in franchises from Star Wars to Dune echoes Kaluza Klein's compactified dimensions, art anticipating science by decades. Even video games like Portal, with its wormhole gun mechanics, teach players to navigate non-Euclidean spaces intuitively, training brains to grasp concepts textbooks struggle to explain. Yet for all its foresight, fiction often stumbles where science thrives. Movies love depicting dimensions as stacked layers, parallel Earths just a portal away. Reality, though, might be far weirder. Hidden dimensions could be fractal or knotted or vibrating in ways no screen could depict. That's the beauty of the dialogue between art and science. One dreams wildly, the other tests ruthlessly, and somewhere in the middle, truth emerges. So the next time you lose yourself in a sci-fi epic, remember, you're not just escaping reality, you're rehearsing for its next big discovery. Visualizing 26 dimensions is like trying to describe a sunset to someone who's never seen color. Our brains simply aren't wired to perceive beyond the three spatial dimensions we navigate daily. But just because we can't see these hidden layers doesn't mean we can't understand them. Scientists and educators have crafted ingenious tools to bridge the gap, transforming abstract math into tangible experiences that spark both insight and wonder. Start with shadows, a concept as simple as it is profound. Hold a coffee mug under a light, and its shadow on the table is a flattened, two-dimensional version of the three-dimensional object. Now imagine that mug casting a four-dimensional shadow in our world. Mathematicians use this exact principle to project higher dimensional shapes into lower dimensions, creating ghostly glimpses of structures like tesseracts, the 4D cousins of cubes. These projections are distorted, incomplete, but they hint at patterns our minds can begin to trace. It's like listening to a symphony through a single earphone. You miss the full richness, but you catch enough to sense the grandeur. Virtual reality takes this further, letting us interact with dimensions we'd otherwise never experience. Apps like Dimensions or Hypernym allow users to rotate 4D objects in real time, watching as their edges twist and fold in ways that defy 3D logic. At first, it feels disorienting, like trying to solve a Rubik's Cube while blindfolded. But with time, the brain starts to detect rhythms in the chaos, patterns that whisper of a reality where left and right aren't the only directions. These tools don't just teach, they rewire intuition, proving that dimensions aren't just numbers in an equation. they're landscapes waiting to be explored. Then there's the power of analogy. Think of a 2D creature living on a piece of paper, unaware of the third dimension. If you reached down and lifted a circle off the page, it would vanish from the creature's world, only to reappear elsewhere like magic. To them, your actions would be inexplicable, but to you, they're trivial. This thought experiment, popularized by Carl Sagan in Cosmos, forces us to confront our own limitations. If a 4D being interacted with our world, their movements would seem just as impossible to us as ours do to that flat circle. Suddenly, the idea of hidden dimensions isn't just plausible, it's humbling. Artists, too, have become essential collaborators in this quest to map the unseeable. Sculptors like Tony Robbins create physical representations of 4D geometry, using wires and mirrors to simulate how a hypercube might intersect our space. Mathematician Henry Seligman's 3D printed shadows of higher dimensional knots reveal symmetries invisible in lower dimensions, turning abstract algebra into objects you can hold in your hand. These creations aren't mere models, they're portals offering a tactile way to grasp concepts that equations alone can't convey, the most thrilling part. These tools aren't just for experts. YouTube channels like PBS Spacetime and Veritasium use animations, games, and even origami to unpack dimensional theory for millions. When a high school student folds a Möbius strip a surface with only one side, they're touching the edge of topology, the study of shapes in higher dimensions. When a gamer plays 4D toys, they're training their brain to navigate spaces that textbooks describe only in symbols. This democratization of higher dimensional thinking is revolutionary. It means the next breakthrough might not come from a lab, but from a teenager playing with virtual tesseracts in their bedroom. So while we may never see 26 dimensions directly, we're learning to feel their presence through shadows, simulations, and the sheer stubborn creativity of those who refuse to let math stay on the page. Every time we project, animate, or sculpt the unseeable, we're not just teaching. We're reminding ourselves that the universe's deepest truths are often hidden in plain sight, waiting for the right tools and the right minds to bring them into focus. The hunt for hidden dimensions is entering its most thrilling chapter yet, with a new generation of experiments poised to turn speculation into discovery. Imagine gravity sensors so precise they could detect the weight of a virus, instruments like the upcoming Einstein telescope, a gravitational wave observatory buried deep underground to shield it from Earth's vibrations. This colossal machine won't just listen for black hole collisions. It could catch whispers of extra dimensions in the way spacetime ripples. If gravity truly leaks into higher dimensional space, subtle anomalies in these waves, echoes that don't match predictions, might betray the presence of realms we've never seen. It's like tuning a radio to static and suddenly hearing a faint, unfamiliar station bleeding through. Meanwhile, particle colliders are pushing energies to unprecedented heights. The proposed future circular collider, a 50-mile ring beneath the Alps, would smash protons with 7 times the force of the Large Hadron Collider. At these extremes, physicists speculate we might create micro-black holes, fleeting, quantum-sized distortions that could evaporate in a flash of Hawking radiation. Their lifespan and decay patterns could reveal whether gravity strengthens at tiny scales, a telltale sign of hidden dimensions. Picture throwing a pebble into a pond and watching the ripples. If they spread differently than expected, it hints at hidden currents beneath the surface. But you don't always need brute force to uncover subtle truths. Tabletop experiments are chasing extra dimensions with devices small enough to fit in a university lab. Quantum sensors, like those using ultra-cold atoms or diamond defects, can measure gravitational forces at micrometer scales precisely where extra dimensions might warp spacetime's fabric. If gravity deviates from Newton's inverse square law at these distances, it could mean we're brushing against the edges of a curled-up dimension. Think of it as running your hand over a seemingly smooth table, only to feel the faintest bump of a seam no one knew was there. Space missions are joining the fray too. The Laser Interferometer Space Antenna, or LISA, will launch in the 2030s to detect low-frequency gravitational waves from supermassive black holes. These cosmic behemoths, with their extreme warping of spacetime, could serve as natural laboratories for testing whether gravity behaves oddly near their event horizons, another potential fingerprint of higher dimensions. It's like studying the swirls in a cup of coffee to deduce the shape of the spoon that stirred it. The boldest ideas sound like science fiction but could soon be science fact. Some theorists propose using quantum entanglement itself as a dimension detector. If particles remain connected through higher dimensional shortcuts, subtle statistical quirks in their behavior might reveal the unseen geometry linking them. Others suggest repurposing neutrino detectors, which already track elusive particles, to hunt for anomalies that could indicate particles briefly disappearing into other dimensions. Even the cosmic microwave background, the afterglow of the Big Bang, might hide clues. Certain patterns in its temperature fluctuations could be scars from primordial brain collisions, cosmic birthmarks from a multidimensional beginning. What unites these efforts is a shift from speculation to precision. For decades, hidden dimensions lived in chalkboard equations and thought experiments. Now they're becoming targets, real, measurable phenomena that could emerge from noise as technology sharpens our vision. The stakes couldn't be higher. A single anomaly, one stubborn data point that refuses to fit the old rules, might crack open reality's deepest secret, that we've been living in a cosmic hall of mirrors all along, surrounded by dimensions we're only now learning how to see. The next generation of explorers won't need telescopes or rockets. They'll need patience, creativity, and the courage to follow the math wherever it leads, even into the unseen. Discovering that our universe is just one layer in a vast multidimensional tapestry wouldn't merely rewrite textbooks, it would force us to confront existential questions we've barely begun to articulate. Imagine the Copernican revolution, but on a cosmic scale. First, Earth was dethroned from the center of the solar system. Then the Sun became just one ordinary star among billions. Now picture learning that even space-time as we know it is a shadow of something far grander. Would this revelation shatter our sense of significance or paradoxically amplify it? History suggests both reactions are possible. When Galileo pointed his telescope at Jupiter's moons, it didn't just expand our understanding of the heavens, it sparked a cultural earthquake, challenging the dogma that humanity was the singular focus of creation. Yet instead of diminishing us, that humility birthed modern science, proving that facing our smallness can be the very thing that elevates us. But hidden dimensions introduce a twist Galileo couldn't have imagined. If we're surrounded by realms we can't perceive, does that make us prisoners of our limited senses or pioneers on the threshold of an unimaginable frontier? Philosophers have long debated whether reality is all we can observe, a concept called empirical realism, or if there's a deeper thing in itself lurking beyond perception, as Kant proposed. The discovery of extra dimensions would tilt this debate decisively, proving that the universe operates on rules our biology never evolved to grasp. It's like ants tracing patterns in the dirt, unaware they're crawling atop a buried cathedral. The awe of such a realization could unite science and spirituality in unexpected ways, reframing ancient questions about the nature of existence through the lens of cutting-edge physics. Then there's the ethical weight of this knowledge. If higher dimensions exist, could we ever interact with them, or worse, damage them? consider how carelessly we've treated our own planet, only to later understand ecosystems' fragility. Now extrapolate that to a multiverse. Theoretical models suggest that colliding branes, those hypothetical higher dimensional membranes, might spawn new universes. But if civilizations in one dimension could influence another, even accidentally, the stakes become staggering. A lab experiment in our 3D world might ripple into a 5D realm with catastrophic consequences we'd never foresee. The precautionary principle would take on new urgency, forcing us to ask not just can we, but should we, before probing too deeply. Yet the most profound shift might be in how we view intelligence itself. If consciousness is a product of our 3D brains, could beings in higher dimensions experience thought in ways we can't fathom? Mathematicians struggle to visualize 4D shapes. How could we begin to comprehend 4D minds? Conversely, if we're fundamentally incapable of perceiving these dimensions, does that place a hard limit on human understanding? Some theorists argue that AI, unshackled from biological constraints, might bridge this gap, deploying hyperdimensional logic where our linear reasoning fails. But that raises another dilemma. If machines surpass us in grasping the universe's true nature, does humanity become secondary in the story of cosmic discovery? Perhaps the answer lies in embracing both humility and ambition. Learning we're embedded in a multidimensional cosmos wouldn't erase our achievements, it would reframe them. Every equation we've derived, every probe we've launched, would become proof that even confined to a slice of reality, we've pieced together fragments of something infinite. That's not insignificance, it's a testament to curiosity's power. The universe may hide its deepest layers, but it also leaves clues in the whisper of entangled particles, the grip of gravity, the math that insists on 26 dimensions. And if we're the species bold enough to follow those clues, then our place in the cosmos isn't diminished by what we don't yet know. It's defined by our refusal to stop searching. Hidden dimensions don't just belong to physicists, they're a playground for minds of all disciplines, each interpreting their mystery through a different lens. Mathematicians, for instance, don't merely count these extra dimensions. They explore their shapes, probing how they twist and connect in geometries that defy ordinary intuition. Take topology, the study of properties preserved through stretching or bending. A donut and a coffee mug might look nothing alike, but to a topologist, they're identical, both have one whole. Now imagine that logic scaled up to 26 dimensions, where donuts become Kalabi-Yau manifolds, and the holes are gateways to understanding how particles acquire mass or why gravity behaves the way it does. It's not just about solving equations, it's about mapping the invisible architecture of reality itself. Artists, too, have wrestled with higher dimensions long before string theory made them fashionable. Picasso's Cubist paintings shattered the illusion of a single viewpoint, showing objects from multiple angles at once. A crude but powerful attempt to hint at dimensions beyond our perception. Then there's M.C. Escher, whose impossible staircases and infinite loops play with geometry in ways that feel alien yet eerily familiar. His Circle Limit series, where fish shrink and grow as they near the edge of a disk, is a 2D projection of hyperbolic space, a realm where parallel lines diverge and angles don't add up the way they should. These artworks aren't just pretty illusions, they're training wheels for the mind, teaching us to see beyond the limits of our three-dimensional instincts. Philosophers, meanwhile, grapple with what these dimensions mean for our understanding of existence. If reality has layers we can't perceive, does that make our everyday world an illusion, or just one slice of a grander whole? The ancient allegory of Plato's cave, where prisoners mistake shadows on a wall for reality, feels hauntingly relevant. Are we like those prisoners, oblivious to the higher dimensional truths casting shadows we call laws of physics? Some thinkers argue that hidden dimensions challenge the very notion of objectivity. If our senses and tools are confined to 3D space, can we ever claim to know the universe's true nature, or are we forever stuck interpreting its echoes? This interdisciplinary dance isn't just academic, it's how breakthroughs happen. When mathematician Emmy Noether proved that symmetries in equations correspond to conservation laws like energy or momentum, she didn't just advance abstract algebra, she gave physicists a Rosetta Stone for decoding the universe. Similarly, when digital artists today render 4D objects in virtual reality, they're not just creating eye candy, they're building intuition pumps for future scientists. Even music gets in on the act. The harmonics of vibrating strings mirror the frequencies theorized in string theory, as if the universe has its own hidden soundtrack waiting to be heard. The beauty of this collaboration is that no single discipline holds the full picture. Physicists crunch numbers, artists spark imagination, and philosophers ask the uncomfortable questions that keep science honest. Together, they remind us that the biggest mysteries like why 26 dimensions, or what lies beyond our perception, aren't puzzles to be solved in isolation, but conversations to be shared across the boundaries of human thought. So whether you're sketching a hypercube, calculating its volume, or pondering its existential weight, you're part of a tradition as old as curiosity itself, reaching beyond the visible, one dimension at a time. As we've journeyed through the labyrinth of 26 hidden dimensions, one thing is clear: the universe doesn't just defy our expectations, it shatters them. What began as a mathematical quirk in string theory has blossomed into a revolution, forcing us to confront the unsettling possibility that everything we see, touch, and measure might be a fraction of a far grander reality. Whether these dimensions exist or remain elegant abstractions, their pursuit has already reshaped science, art, and philosophy, proving that the act of questioning is as transformative as the answers themselves. Consider how far we've come. A century ago, the idea of curled-up dimensions was dismissed as fantasy. Today, it's a cornerstone of cutting-edge physics, inspiring experiments that probe the fabric of space-time with unprecedented precision. The skeptics aren't wrong to demand proof, but history shows us that today's heresy often becomes tomorrow's textbook. Black holes were once deemed mathematical oddities until we photographed one. Quantum entanglement seemed impossible until it powered encryption. The lesson: reality rarely caters to our comfort, yet the true magic lies not in the destination but the journey. Each failed experiment, each recalibrated theory, is a stepping stone toward deeper understanding. Maybe hidden dimensions will remain forever beyond our grasp, like a melody played in a frequency only the cosmos can hear. Or maybe one day a gravitational wave will ripple with an anomalous pattern, a particle will vanish where it shouldn't, and the veil will lift just enough to reveal a universe vaster than our boldest dreams. That's the heart of science, not certainty, but curiosity. Whether you're a physicist chasing equations, an artist sketching hypercubes, or simply someone who gazes at the stars and wonders, you're part of this grand exploration. So stay restless, stay hungry. The next breakthrough might come from a lab, a telescope, or the comment section below. Speaking of which, if these ideas sparked your imagination, let us know. Hit like if you want more deep dives into the cosmos' wildest mysteries. Subscribe to join us on the next adventure, and share this video with anyone who loves to question the nature of reality. Until then, keep searching. The universe has secrets left to tell, and you might just be the one to hear